Hey guys, in this video we're gonna look at some theorems of continuous functions. Remember in the last few videos I've already mentioned what is a continuous function, right? Simply we verify a continuous function by verifying whether every point of the function is continuous, right? So we'll recall the continuity of a point in the function. So if the function, let's say fx, if its limit at that point is equal to, if the limit exists and its value is equal to the value of the point at the value of x at that point, the value which is fx, right? If its limit is equal to fx, then we said the function at this point is continuous, right? So if every point of the function is continuous, then the function is itself a continuous function. Okay, but actually it is a theorem of continuous function, or it is also another way to verify whether a function is continuous. So let's say this theorem, it says a mapping F of a metric space S X into metric space Y is continuous if and only if F inverse V is open in X for every open set V in Y. That is to say, like if we are having X and Y, now F maps X into Y, right? How are we going to verify if F is a continuous function? If take any like open set V in Y, then its inverse F inverse V is also open, then the mapping F, the function, is continuous. Or conversely, if we're given that this function F is continuous, then we will know that if you take any like open set V in Y, then its inverse F inverse Y, F inverse V is also open. Okay, so how are we gonna prove it? First of all, we wanna prove we wanna show that given a continuous function, we want to show that the inverse FV is open. So let's first find, or let's first fix, or let's just choose an open set V in Y, right? How are we gonna prove it's open? By its definition, we know that to prove it's open, we're simply proving that every point of the set F inverse V is an interior point, right? So let's see it. Suppose now we have F continuous on X, and we take an open set V in Y. We want to show the inverse of V is open. That is to say, every point of the inverse of the inverse F of V is an interior point, right? So now let's suppose we take arbitrarily, actually not arbitrarily taken point, but let's first suppose we have a point P in X, and we know that FP is contained in V. So simply F maps the point P into V, the set that we just choose. And now V is open, right? So according to its definition, we know there exists some epsilon larger than 0 such that the distance between FP and Y is smaller than epsilon, right? So V is open, since V is open and FP is contained in V, then there will be a small ball around centered at P. and there will be so the points in that ball which has distance less than epsilon means that this point is also contained in V, right? Because V is open. Okay, so this is the first condition that we use. The second one is we know that F is continuous at P, right? So by continuity, there exists delta that larger than 0, such that the distance between x and p is, when the distance between x and p is smaller than epsilon, we have, that implies fx and xp, the distance between these 2 points is smaller than epsilon, right? So I think I just, so the distance between x and p is smaller than delta, implies the distance between fx and fp is smaller than epsilon. This is simply the definition of continuity. Okay. So as long as we take the distance between x and p smaller than delta, we found that x is contained in the inverse of V, right? That is to say, F inverse of V is open, right? Because you are simply saying that the point is interior. You are simply proving that the point is interior points. It is contained by a smaller. You can find such epsilon, right? You can find such an epsilon such that you choose a ball centered at x with like a radius of epsilon, and that ball is totally contained in V, in the inverse of V, right? Inverse of FV. Okay, so conversely, we prove it in another. We prove from that every open set V in Y can have taking every open set V in Y, we know that F inverse of V is open. From this condition, we try to conclude that the mapping F is continuous. So how are we gonna do that? Simply now let's suppose F inverse of V is open in X for every open set V in Y, right? This is a condition. And well, first of all, still we fix a P. We fix a P in X and epsilon larger than 0, and we choose V. We choose V be the set of all Y, be the set of all elements Y that is contained in the capital Y, such that the distance between Y and FP is smaller than epsilon. So V is a set that containing all the points containing all the points in the ball which centered at FP with distance with radius epsilon, right? So V is open, right? V is open because it contains all its interior points, right? And we also know that the inverse of V, the inverse of FV is open. That gives us that there exists a delta, right? Delta such that such that x is contained in the inverse of FV as soon as the distance between P and X is smaller than delta. Is that true? Well, it is because we know the F inverse of V is open, right? It means all the points of it is a interior point, right? So if you So now we're taking delta. So now there exists a delta, and under such delta with certain delta, we know that the points in that small circle are all interior points. So such points x must be contained in F inverse of V, right? Okay, but another thing we know is that if x is contained in F inverse of V, then fx must be contained in V, right? Because it maps x to fx, right? So now we get the conclusion that the distance between fx and fp it will be smaller than usual, right? Okay. So that is to say f is continuous, right? Because you're simply saying that for x that is for you firstly choose a set V, and you find that those x that will be mapped into the set V are all continuous, right? So f is continuous on all the points that will be mapped into V that you choose, right? So every open set V in Y is also open. So that is to say every point f is continuous at every point of x, right? So f is continuous function. Okay. Let's take 1 or 2 minutes to rethink of the problem, rethink of how we organize the proof. So in the first step, we want to show the inverse of f is open. So we further want to prove by every point of f inverse of V is an interior point. This is basically the structure the key point of the first proof. And the second one, we want to show it's continuous, right? So the function is continuous means by its original definition, that means the function f is continuous at every point. Okay, and the first thing you do is to first choose V, and you have to verify the set V you choose is open, right? Or it can't be applied to the condition that the inverse of f is open. Okay. So by choosing such kind of V, you're actually looking for the corresponding x, right? And you show that, and you continue to show the function f at all these points x is continuous. Okay, this is basically how we prove the first theorem. So it has a corollary. That is to say, a mapping f of a metric space x into a metric space y is continuous if and only if. Well, now we consider, instead of open, we think of the problem on the closed sets. If the inverse of inverse of f say is closed in X, for every closed set say in Y. But it's pretty much a similar thing with the open case, right? Because we know a set is closed if and only if its complement is open, right? And also we know that, well, the inverse of Fe of its complement is equal to the inverse of E of the whole thing, the complement of the whole thing, right? So the proof is pretty much the same, except you are there is one more step to convert closed into open. So I'm not gonna prove it in this video, but you can just make a draft in your head, in your brain, and it's pretty much the same. So let's move on to a next theorem. It says, well, suppose F is a continuous mapping of a compact metric space. Oh, I'm sorry. So, first item, F is continuous mapping. Second one is a compact metric space. Then Fx is compact. So we have two conditions. The first is F is continuous. The second is its domain is a compact metric space, and we verify that the conclusion of the theorem says Fx is also compact, and Fx is certainly contained in Y, right? And how are we gonna prove that? Remember, what is compactness? How are we gonna prove compactness? And I don't know if you still remember one thing about open cover. So if Fx a set is compact, if it is contained in finite many, it is contained by a finite open cover, right? But what is open cover? Do you still remember open cover? So let's see. Open cover is simply the union of, well, suppose V alpha is an open cover, then the union of V alpha must contain X, the set that you wanna cover, right? And the proof for this theorem is also very simple and straightforward. So first of all, let's choose an open cover of Fx. Okay. Well, we don't know if it is compact, right? So that is to say, we don't know if there exists finitely many V alpha that can cover Fx, but we can still choose open cover, a set of open cover that a sequence of open cover. A sequence of V alpha that covers Fx, right? And we know that F is continuous. That is to say, each of the inverse of F V alpha is open, right? This is what we just showed in the last theorem, right? Well, because it's open cover, so V alpha must be open, right? So the inverse of F V alpha is also open. And another thing that we have is X is compact, right? So there are finitely many indices, that is simply means, well, alpha 1 to alpha n is finite, and X is compact, right? So X can be contained in F inverse V alpha 1 union F inverse V alpha 2 blah blah until union F inverse V alpha n, and there exists finitely many indices alpha n. Okay. So what's next? We know that if we do another mapping after f inverse of E. So for every E in Y, E means an open set. So we just use another notation E because it's a general case. It's a general case. It's not the case that we specify like V alpha, right? So generally, for every E in Y, if you take you first take the inverse of f of E, and take another mapping it again. So f inverse of E is also contained in E, right? Because every time you're taking the mapping or its inverse, it's like every time you taking the mapping of f, it's like shrinking its like shrinking its radius or shrinking its range shrinking its range of values. Okay, so what we know is that, well, x can be covered by f inverse of v alpha until f inverse of v alpha n. So fx can be covered by v alpha 1 union v alpha 2 until union v alpha n. So you are simply taking the mapping f for all the sets here, right? So finally, we prove that fx is compact, right? Because now alpha n is finite. Now there are finitely many open sets, open cover. Okay, so this is basically the case. Okay, still I have another theorem that we will talk about in this video. Well, it is also called Weierstrass Theorem. It's very useful or practical in continuous function. It's basically you will use it again and again in your in your following study. And many of you might already say this theorem in your high school. But we did, or calculus, but we didn't prove it rigorously. Sorry, in a mathematical analysis style, and the proof is actually very simple and very straightforward. And you say I only wrote 2 lines here because well, if you really wanna write all the things about the proof, well, you need not only these simple 2 lines, but just a hint or just the basic structure of how we are gonna prove this theorem. So now suppose f is continuous real function on a compact metric. Okay, still we have 2 conditions. The first thing is f is continuous real function. Okay, and the second condition is that it is on a compact metric space X. And suppose we have M, the supremum of Fp, well, P is contained in X, and the little m, infimum of Fp, well, P is contained in X. And you know that when P is contained in X, the supremum is actually its maximum, and so is infimum is actually its minimum, right? So there exists points PQ in X such that Fp equals its supremum and Fq equals its minimum. Or in other words, as we just said, PQ is actually contained in X. So in other words, F attains its maximum and minimum, right? And the idea of the proof is that, well, we know that F is continuous and X is compact. What we get is that fx compact by the previous theorem, right? And a compact set fx means it's bounded and closed, right? In the previous videos, I remember I mentioned that compact means bounded and compact set means a bounded and closed sets, and well, you know it is bounded, right? It's bounded and closed means it must contain its supremum and infimum, right? Or well, you first say if it's bounded, then it must be contained in certain like interval, right? And it is also closed, so I can actually shrinking its bound until the points are the points of its maximum and infimum are exactly in the set X in its domain, right? Because it's closed. I can't find such points. I don't remember if I mentioned certain theorem before, because I remember if you have bounded and closed set, you can actually directly get that F contains its supremum and infimum. Okay, I'll check this, and if there's not, maybe I'll mention it in the following videos. So that's basically what I want to talk about in this video, and I know it's been like 2 or 3 weeks since the last time I uploaded my videos, simply because I moved to Liverpool to start my year 2 in Liverpool. But actually I have spent 2 years in university, so it's my 3rd year as a university student. But in Britain, I'm still like a year 2 student. So, well, I have to do a lot of like settle down things, and finally the first week starts, and now I have some time to reconsider about how these videos are gonna like heading for, and simply because recently I didn't find much like things or theorems that not only interest me, I mean, even there are some like so interesting or fascinating theorems, I am not confident enough to like present it to you guys, to those who watch my videos. So that's basically why I didn't upload last like 2 or 3 weeks. So I'm sorry for that if you really like follow my videos, but maybe later on, I'm not sure I will like upload once a week, but I'll try my best. And maybe sometimes if it's so sometimes if I met like or come up with some ideas or theorems, or no, I cannot come up with theorems, I'm sorry. If I come up with some ideas, or I met some like interesting, fascinating theorem that I want to share with you guys, maybe I'll update like 2 or 3 times a week. That's possible, right? So that's all for today's video, and thank you all for following me and watching my videos. If you have any like questions or advice, please comment in the comment bar and or send me emails. Okay, bye bye.